Okay, now let's solve log base 3 of 2 plus log base 3 of 20 minus 2x equals log base 3 of 10x minus x squared. You might look at that and it's super tempting to turn the left side into log base 3 of 2 plus 20 minus 2x. We can't do that. You can't distribute logs, and I guess if this is sort of the backwards of trying to distribute logs, distribute in quotes, so factor, I guess, in quotes. You can't factor logs like this. That's not applying the formula we had just learned. Right? So this is a common mistake that occurs to try to turn log base 3 of 2 plus log base 3 of 20 minus 2x into log base 3 of 2 plus 20 minus 2x. Can't do that. All right? Instead, apply the law of logarithms that we looked at. So the right side stays the same, but the left side is converted using the first law of logarithms into log base 3 of 2 times 20 minus 2x. Now that we have a single log on each side, earlier we didn't. We had two logs on the left side. We had a log base 3 plus a log base 3. But now that we have a log base 3 on the left side and we have a log base 3 on the right side and nothing else, we can set the inputs to the logs equal. No slashes again. I hope you see why no slashes. We cannot think of trying to distribute or undistributing that as factoring logs. Those are made up. It's not correct. So we set the inputs to the logs equal. So the input to one log was 2 times quantity 20 minus 2x. The input to the other log on the right side was 10x minus x squared. So we set those equal. Now we actually have a quadratic equation. I mean, it's easier to spot, I guess, once you distribute the 2. So 40 minus 4x equals 10x minus x squared. Add and subtract terms on both sides to have a 0 on one side. X squared minus 14x plus 40 equals 0. If the left side doesn't factor, we can always complete the square, but the left side does factor. X minus 4 times x minus 10 equals 0. So we get x equals 4 or x equals 10. Now, the original equation had logs, so we need to check if 4 is a solution or not, and if 10 is a solution or not. So is x equal to 4 a solution? Well, we need to check the inputs to the logs, and there are 3 logs in the beginning. There's this log base 3 of 2, there's this log base 3 of 20 minus 2x, and there's also log base 3 of 10x minus x squared. So the first log input is just the number 2, right there. That's the input, 2. Is that positive? Yeah. You don't have to substitute for x. Yeah? It's just, there's no x to substitute there. Fine, so 2 is positive. The next log input is 20 minus 2x. When we plug in 4 for x, and we get that the input to this log was 12. That's positive. Okay, good so far. 10x minus x squared is the next log input. When you plug in x equals 4 there, you end up with 40 minus 16, and we don't need to simplify that further. We can tell bigger minus smaller. That's positive. Okay, so x equals 4 is a solution. What about x equals 10? Well, again, just to be systematic about it, the first log, the input was 2. Okay, that's bigger than 0. Again, we didn't have any x to have to substitute there. The next log input, when you plug in 10 for x, you have 20 minus 20, which is actually equal to 0. That is not bigger than 0. Recall that the input to a log has to be bigger than 0. So x equals 10 is not a solution. So the second log here, its input caused a problem. We didn't even spend any time checking the third log. Okay, we already checked the second log. That's enough to say 10 is not a solution. So 4 is the only solution. Let's do another example. Log base 6 of 4 plus log base 6 of x plus 5 equals log base 6 of 8. So using the first law of logs, we can rewrite the left side. Log base 6 of 4 times quantity x plus 5 equals, the right side stays the same, log base 6 of 8. Now that there's a single log on each side of the same base, we can set the inputs equal. So 4 times quantity x plus 5 equals 8. 4x plus 20 equals 8. 4x equals negative 12. X equals negative 3. Is x equals negative 3 a solution? Well, we need to check, go back to the original equation, check the input to each log. So for the first log input is just a 4. That's positive. Okay, that's fine. We didn't have to, there's no x to substitute there. Okay. The next log input is x plus 5. If you plug in negative 3 for x, you have negative 3 plus 5, which is 2, which is positive. Okay, that's good. The next log's input is 8. I've highlighted it there in red. That's positive. There's no x to substitute. Great. So x equals negative 3 is a solution. So look, by using x equals negative 3, each log's input was bigger than 0, so x equals negative 3 is a solution. Whether x itself is positive, whether x itself is bigger than 0 or not, does not matter. What matters is whether the input to each log is bigger than 0. Okay, let's at this point clarify something about checking solutions, because we've seen a number of situations throughout the semester where you need to check solutions. So let's just first clarify settings where you may or you should check solutions to an equation. Anytime. You have an equation you've solved. You can check solutions. You can check your work if you have extra time on a quiz or a test. What you're checking for, I guess, is does the value of x make the original left side equal to the original right side? Why would you check? Well, because if it doesn't work out, maybe the issue is there was a mistake earlier in some step, and this gives you a way to maybe detect that there was an error. Okay, so I'm using this language carefully. Situations or settings when you may check or when you should check. It's really any time. But just to use a different word here, there are settings or there are situations when you must check solutions to an equation. So what are those situations? I can think of three. One is when the original equation has logs in it. Okay, if your original equation has logs, then first of all, what are you checking for? You're checking that the input to each log must be positive. If you square both sides of an equation, then you must check. What are you checking for? It's really the same check as earlier. Does the value of x make the original left side equal to the original right side? Why are you doing this check, though? It's because squaring both sides can create false or extraneous solutions. There's one other setting in which you really must check solutions to an equation, and that's if a variable appeared in the denominator of a fraction. So if you have like x hanging out in the bottom of a fraction, you should check, does the value of x you have make any of the original denominators become 0? Because when you start working with equations, when you start manipulating equations with fractions, this can also create false or extraneous solutions. So those are the three settings in which you must check, but you could always check just to help see, snuff out if you had any errors occur earlier.